Hi kids, welcome to our first content video of the year and certainly of this week. So we're going to start with something that you probably should have seen in pre-cal, the dot product. We didn't really use the dot product in calculus so much, that in single variable calculus, but we're going to use it a bunch here in multivariable calculus. So in 3D space, right, you probably did the dot product in 2D space. Well, the formula for 3D space isn't really any big deal, right? Just adding the third piece there. And remember that the dot product is denoted by that dot in between two vectors, A and B, right? I should be better with my notation. Sometimes vectors, right, have a little thingy over them like this, or sometimes in some books you'll see hats. I don't know, whatever. Or sometimes they're just bolded, okay? The dot product of two vectors, right, is a number, don't forget, is a scalar, right? A number, a value. So sometimes the dot product is called an inner product. I don't use that much, but I think your book does. So the inner product or the scalar product, I use that more. I think of the dot product as a scalar product. So this, if you're in physics now or have taken physics, you'll recognize this formula for the dot product. If theta is an angle between vectors A and B, then the dot product is the magnitude or the length. And again, sometimes magnitude depending upon the book or the website. Sometimes you'll see magnitude with these double bars. Sometimes you'll see them with the single bars. But the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. If I isolate cosine, I don't know why my dot is so dramatic there. If I just do algebra and isolate cosine there, you can see that I get a fraction of the cosine of the angle between two vectors is the dot product divided by the product of their magnitudes. Now, in particular, hopefully you can see that if the cosine of pi over 2 is 0, right? So if the cosine is pi over 0, right, and pi over 2 is 90 degrees, right, perpendicular, then these lengths don't matter and the dot product is 0. Orthogonal is just another word for perpendicular. So, and again, maybe in physics, I'm going to do some very pathetic, let's suppose I have some car here. It looks like this. You're most often in physics, you're dealing with force, right, of vectors. And I want you to think of the dot product, right? The dot product is how parallel are two vectors, right? That's what the dot product means. How parallel are they? A number to describe, right? Because it's a number. How parallel are they? So for example, if you have perpendicular lines, right? Well, they are not parallel at all. Zero parallelness, right? And why you care about that is, well, if, for instance, somebody is, right, if you're pulling this cart, right, to the left, and I'm said, oh, I'll help you, and here I am standing on the top, but I'm pulling straight up, how much am I helping you move, right, move this cart to the left, right? Thanks, Miss Getz, you ain't no help at all, right? So, however, if I am standing instead, and if I'm able to pull if I'm able to help you by pulling like this, right? Pulling along, I'm helping you some, right? But how would the best help? The best help would be is if I stood right beside you, and pulled along completely parallel to you, right? So remember, in physics, work is equal to, right, force times direction. Well, this, right, is really, right, if that physics messes with you, don't, and again, I'm such a neophyte at physics, but to the best of my understanding, this is what you're actually trying to figure out. With the dot product gives you some kind of number where you can see how parallel are the two vectors in relation to the angle between them. All right. Direction angles. So this is an idea of a vector in 3 space, right? So here I am with a vector in 3 space, and that's vector A, right? So it's out here, and I went out the X, out the Y, and up the Z axis. And I want to know about the kind of like the components of that vector, right? So in relation to their angles. So I'm trying to nail down by angle, where is this vector in space? So direction angles, think of this as A, B, and C, alpha, beta, gamma. And I'm only talking about angles between 0 and 180, or 0 and pi. Remember, we're working radians for the most part, right? Vector A makes with the positive. Direction angles go with the positive X, Y, and Z axis. So here's my vector A in blue, and you can see that alpha, the angle alpha, is from the, right, I, right? Vector I goes with the unit vector along here, along the A. What is the angle here with the positive X axis? How big is that angle? Big or small? And then here with the positive Y axis, or you can think about unit vector J, and gamma, right? So that the direction angles kind of orient you in space by not just the rectangular coordinates, but your rotation from each one of those axes. This GeoGebra applet isn't 100% great, but I do like how, and you can see this is where I got my picture from. I do like the fact that I can kind of drag this around and show you, right? If you can think of, right, can you see the direction angles, right, as I move this? Right, you can see alpha, beta, gamma, all those angles kind of moving along with it, which is kind of cool. Right, nailing down where I am. Now, the cosines of those direction angles are shockingly called direction cosines, or DCs. We're going to use these DCs if somebody needs the direction angles. If we are asked to find direction angles, which you will be in your homework, I'm going to use these direction cosines to get them for me. So I'm going to develop where does this come from? So I'm going to do the dot product with that vector A and the unit vector I, so just in the X direction. So there's my vector A dotted with I, right? And just by the definition of dot product, that's the magnitude of A, the magnitude of I, times the cosine of alpha in between them. So here's the components of A, A1, A2, A3, dotted with the unit vector I. Where did the I go over here? Where did this go? Right, the magnitude of the unit vectors is 1, so there's actually just a 1 in here. Now, what happened to this side? I did the dot product, right? Right? A1 times 1 plus A2 times 0 plus A3 times 0 just gives me A1. And now I'm going to solve for cosine. And then, of course, from here, I can get the angle by using inverse cosine, right? So the inverse cosine, and knowing which quadrant I'm in, don't forget that. And I can use the same thought process to find all three direction cosines. So there's my direction cosine. So if I actually need my direction angles, use your direction cosine formulas and then do inverse cosine. Pretty cool, huh? Now, just because I can show off, look what happens when I isolate the components in each one of these equations. So there's my three direction cosines again. Look what happens if I isolate A1, isolate A2, isolate A3. Then I have A, right? That is the vector A. Now look at my vector on my right side. I'm going to factor out the magnitude. Crazy. Now I'm going to divide both sides of that equation by the magnitude. Wait, what? Check that out, right? Can you think about what that says, right? What's on the left side? That's the unit vector, right? The unit vector for vector A. The unit vector of vector A is the same thing as, well, or its components are, its direction cosines. Gasp, right? The direction cosines of a vector are the components of the unit vector in the direction of that vector. What? Right, math. Sometimes math is just cool. Actually, all the time it's cool. Except for, right, high school geometry is pretty bad. Again, showing off. What if I found the magnitude of both sides of this equation? Right, they are equal, right? Well, what's the magnitude of any unit vector? 1, right? And then finding the magnitude using Pythagoras, right, to find the magnitude here of the direction cosines would be just the square root of the squares of all of that. What happens if you square both sides of that equation? Oh, snap. I mean, NBD. No big deal. All right. Next thing in this section is vector projections and scalar projections. Scalar projections is a number. Vector projection is an actual vector. So look at the diagram below. So if I'm given vector u, and every vector has its horizontal and its vertical component, right? So I've drawn the horizontal component v, and I've drawn the horizontal component w, right? Those are the components that make up, if you add v plus w, you get u, right? V plus w would give me v using vector addition. So the projection of u onto v, so notice what the subscript is, right? The projection of u onto v is the vector that is the horizontal component of any given vector, right? Think of it as a shadow. So kind of sort of think of like if you had some kind of light here, some kind of spotlight. I'm such a terrible drawer. I don't know how to draw a spotlight, right? So if you had some kind of light shining down, well, that's so bad. Light, no, that doesn't look right. Oh my gosh. There we go. Some kind of light shining down here. The shadow of u onto v is what we call the projection. So I want to know what the length of that projection is, and then I want to actually know what are the components of the projection. So I'm going to start with the scalar projection. I'm going to start with the dot product. The dot product of the two vectors u and v, by definition, magnitude, magnitude, cosine theta. And I'm going to draw a theta in here. There's theta, right? So what have I done here? Can you see what I've done there? I've just divided by the magnitude of b, but can you use some right triangle trig and figure out what I've done there? Isn't it true that the cosine of theta is equal to the magnitude of v over the magnitude of u? Isn't that true? Right? Just using, right? Isn't that just adjacent over hypotenuse? So if that's true, look what happens when I multiply both sides by u. I get the magnitude of v, right? So move this over here. That's what this is. The magnitude of u times cosine of theta, that is the length of v. And what did we call v though? We called v, right? V is the shadow of u onto, right? Onto here. And that's what we called the component, right? The component of u shadowed onto v, or the component of u projected onto v. That is a number. So instead of calling it this, you now have a formula for the length of the shadow. So if I've got the length of the shadow, how do I actually get the shadow? Right? I want the vector. How do I do that? Well, how do you get, right? So notice what I've done here. I've taken a length, a number. This is a number, right? This is a value, a length. And I'm multiplying it times the unit vector of vector v, of the shadow. So how a unit vector, remember, has a length of what? A length of 1, but it's of the shadow. And then how long do I want the shadow to be? Well, that's the dot product divided by the magnitude. And that is how I get the projection. Kind of crazy, right? Let me show you a little applet of this as well. Oh, notice here, I mean, you could just write it like this, right? This is, right, magnitude of v times magnitude of v is where I got magnitude of v squared. And then remember this, right? That is your vector v. So vector v, this is a unit vector divided by its magnitude, is its length 1, but multiplied times the actual length of the shadow that I want. Gives me the projection vector. So here's a nice applet here where you can see, like, so I started with vector u is, this red vector is 5a plus 2j. What's its shadow? I'm sorry, the shadow is 5a plus 2j, right? Here's the shadow. So if I take vector v and change it, right? Can you see where it's Pretty cool, right? Ew. And if I change this, right, this is the projection of V onto U. If I change what I want the shadow to be, let's say 8, 4 maybe. And remember, I'm putting a light up here now. The projection of V onto U. This is kind of the opposite drawing of kind of cool. I like it's kind of cute, right? And notice that their notation here is the projection of a V onto U plus this piece here, right? Which is just, right? If this red V is the horizontal component plus the vertical component, well, then the vertical component must be, right, V minus the horizontal, right? So here's the addition of the parallel component, and the perpendicular component gives me the red vector, right? Crazy. All right. So that's it for the first content video. So in class, I will have the warm-up that goes with this PowerPoint, and then I didn't do any examples. I'll do examples when we're live of each that go with each one of these things, and then we'll break out and do homework together. And then you will also have the same kind of issue for the second content video.